I'm Hendrik Sakowsky. I'm working at the Institute for Occupational Safety and Hygiene at St. Augustine in Germany. And today I'll give you a brief insight into the topic of my master thesis, the development of high-volume personal aerosol samplers. I'll begin with a short introduction about the hows, whys, and whats of the topic. Then short overview of the development, the tests I already performed and some of the results, and then I'll finish with an outlook what we're going to do next. So, in the beginning, why are high-volume aerosol samplers necessary? As many of you might know, there are always decreasing limit values for different kinds of substances or for dust. So the respirable dust limit is now by 1.25 milligrams per cubic meter. And if you are sampling with the old systems with between 3.5 or 10 liters per minute, it takes a lot of time to reach those limit values. So there is a necessity for new systems. And if we look at the limit values for hazardous species like carcinogenic metal species, for example, which are even lower, the necessity for higher sampling volumes is rising. So we need airflows greater than 10 liter per minute to reach those limits or these masses necessary in a good amount of time. So what we did was we designed a small set of prototypes. We have 3 different prototypes, and all these prototypes have different numbers and orientations of orifices. And we are testing them according to the DIN norm 13205, which is the norm for the efficacy of aerosol samplers. These are our 3 prototypes we designed. The first one, the cone, is basically an enlarged version of the known GSP 3.5 or GSP 10 liter sampler. The beetle is a hemisphere with different orifices, and the third prototype, the UFO, is like a low-profile cylinder with orifices at the side. All those 3 samplers are working with 47 millimeter filters, and with the glass fiber filters we have a pressure loss of 30 millibar at 20 liter per minute. This allows us to sample large amounts of workplace dust. So the pressure drop, the pumps we're using, the maximum pressure drop the pumps we're using is around 120, 130 millibar. So there's a lot of substance we can sample. All those dust collectors have an aspiration speed of 1.25 meters per second, which is roughly the aspiration speed of humans. And to achieve this, the area of, or the sum of the area of these orifices is the same for all 3 sampler types. So every sampler has the same aspiration speed. For testing, I had the great opportunity to go to the University of Utah in Salt Lake City for the reason that they have a wind tunnel where real life or real size mannequin fits in, and they are also able to achieve wind speeds as low as 0.1 meters per second, which is the low speed that the DIN norm specifies the samplers have to be tested at. And so I had 3 weeks there and tested 4 different dust types with with 4 different aerodynamic diameters. The norm specifies that there have to be 9 diameters to be tested, but because it's only my master thesis and we have 3 prototypes and not every prototype has to be tested in full, I just took 4, tested them at both wind speeds of 0.1 and 1 meter per second, and to see that there is no dependency on the direction from where the air is streaming at the samplers, we use this rotating dummy, so we're independent of direction, wind direction. The variability of samplers and the deviations from the nominal flow rate are tests that will be performed and aren't performed yet. So I'll give you some of the results of the previous tests. To see if the samplers have the same efficacy as the old models, we're testing them against some reference probes. These are the results in comparison to the reference probes. And we're testing them against the GSP 3.5 liter system. And as you can see, if we take the reference probe at the reference at 1.0, we have differing results, not only for every sampler, but also for the different diameters. These are some effects we have to investigate further, but as we can see, in the smallest diameter tested, 9 micrometers, at low wind speeds on the right side, they're matching really good to the reference probes. For some reasons we don't know yet, if we double the diameter, they are oversampling, and if we then double the diameter again, they are hardly undersampling. So these are some things we observed, and we have to go into deeper details. But for higher wind speeds, we come closer to the reference values for all 4 diameters investigated. And if we compare it to the GSP 3.5 liter system, we have an oversampling on all 4 diameters for the low wind speeds, which isn't that big of a problem. And for the 1 meter per second, we have also take a deeper look into it, because we seem to have a low undersampling area in the middle, or not undersampling, but compared to the highest and the lowest aerodynamic diameter. And this is what we have to do, take a closer look at. But because we are just trying to find the one model that fits best, it's not so bad. Because if we take a look at the values and the deviations from reference probes and from the GSP 3.5 sampler, we can see that for the highest wind speed in comparison to the 3.5, we have undersampling or oversampling for all diameters, but the values for the UFO sampler are relatively close to those values observed with the reference probes and with the old GSP 3.5 system. So we have now prototype we're going to investigate further and look into the future more, how we're going with it. As an outlook for the future, we will repeat those experiments performed in Salt Lake City at our own wind tunnel. This is for different reasons. One of the reasons is to double check if those results are valid. The other reason is we have a smaller wind tunnel. So the wind tunnel in Salt Lake City, as I said, is a real life 1.2 times 1.2 meter wind tunnel, and our wind tunnel is 0.8 meters. So we have a reduced mannequin inside this tunnel, and when we can try, when these results are the same, we can say that it's safe to use reduced size models and reduced size test wind tunnels to achieve the same results. So we have the comparison of the US measurements versus the German measurements. We will compare the results with the different separation functions for respirable and inhalable fractions. We will evaluate the comparability, original size versus reduced size, wind tunnel, and because our wind tunnel isn't capable of the 0.1 meter per second, we have a still air chamber, and if we can repeat those results in our still air chamber, we can also safely say that wind speed in a wind tunnel, or low wind speed in a wind tunnel, can be reproduced in a still air chamber, and so is the opportunity for other institutes that are testing dust samplers to have the same possibility even if they don't have a wind tunnel for it. So to be according to the norm, we will, with the prototype, the UFO, repeat the experiments with 5 more aerodynamic diameters, and have already selected the most suitable sampler. And to fulfill the norm, we have to do some other testing, so intra-model testing, where we have right now 2 prototypes of two prototypes of each model, and produce more to test the inter-model comparability, deviations. And of course, we have to calculate the total measurement uncertainty for the whole method if we are ready for it. So, thank you for your attention.
Are there questions on this early morning?
I'm Fabio Bocconi from INAIL, Italy. My question is related to the aspiration pump that you used, which flow they have, and if you test different flow rates.
Thank you. The pump we used is the PP20 from Dr. Stremming. This not yet on the market, so it's also part of our testings. It has an airflow between 10 and 20 liters per minute, so it's very variable in this area, and from size and weight factor, it's not much bigger than the GSA pumps, and weight is just roughly a kilogram. So it's possible to wear for a longer time and not being too reduced in handling capabilities.
Thank you for our presentation. Flem Deacon from the INRS. It's usual to compare sampling efficiency against a conventional fraction for sampling. Have you planned this kind of test? I mean, inhalable fraction, respirable fraction, and so on?
Yes, those tests are planned because they are also part of the DIN norm and what the DIN norm says. So we will definitely do those tests, but first we have to choose one prototype we're going further with.